when we talk about batteries. So one thing we need to understand is that battery the first four are the parts of the battery, then comes to yes. So the role of anode and cathode keeps changing in a battery upon charge and discharge cycle. But to avoid that confusion, we just consider the what happens in the discharge cycle. That's why you talk in terms of oxidation. Yeah. Okay. So where was I? Yeah. Capacity is the amount of energy a cell can deliver, a cell or a battery can deliver upon a complete recharge. Energy density is the volumetric storage density of a battery. That is per liter of the battery used, per liter is in the volume of the battery used, how much energy it can deliver. And power density is similar with respect to power. So cycling is the process of charging and discharging a battery. So we have a concept called cycle life, which tells us how many times a battery can be efficiently charged and recharged again and again. So all batteries will have a set life. So it's not that you buy a phone and you can charge and discharge it forever. At some point, the battery is bound to fail. And then comes solid electrolyte interface. So when we construct a battery, it's not that there are no reactions taking place inside as such. So there are some reactions that take place. The lithium basically reacts with the electrolyte material, and they form multiple compounds and matrices which act as a passivating layer between the electrode and the electrolyte. But it's not a major concern because it's still an ion conducting passivation layer, so it's not insulating to ions. So capacity fading is the reduction of battery capacity upon cycling. So because the SEI keeps growing and the active material keeps reducing, which in turn reduces the capacity. Self-discharge is a process in which uh, even if we don't connect any load to the battery, it's still there are some internal reactions going on. So that's inevitable, but this loss is recoverable. So if we recharge a battery, we gain back the lost active material. Okay, so diving to lithium-ion batteries. So why the buzz? Why has it like tremendously changed the way of energy storage? Is that as we know, all the devices we use today are smartwatches, mobile phones, other wearables, and we have like skateboards and other things which use batteries. So all these were possible because of lithium-ion batteries. So we can see in the diagram there's a graph. So that's a Ragon plot that shows the comparison between different battery architecture. So in the beginning, we had lead acid batteries, which were quite bulky, and despite the bulk, it wasn't delivering the necessary energy and power. And it evolved to nickel cadmium battery. Then we have nickel metal hydride batteries, and finally we have lithium ion batteries, which is we can clearly see that it has surpassed all its predecessors. So so all the smart technologies rely on being compact and durable and efficient, and lithium ion battery sort of delivers to all these needs. So practically achieved specific energy density for lithium ion battery is close to 350 watt hour per kilogram, and energy density is 314 watt hour per liter. advantages of all this was possible because of lithium. So lithium is a very potent material when it comes to energy storage, owing to its high capacity and low electrochemical potential. So these are typical batteries which have been used and are being used in vehicles. So we first had lead acid battery. You might have seen ads like 20 years ago. We had batteries like Amaron and Exide in which we had to change the distilled water at times. So those were all like lead acid batteries. And then came nickel metal hydride batteries, and finally lithium ion batteries. So we can see, compare the different parameters, and we can see how much better lithium ion batteries are compared to the previously used batteries. So now, if you consider uh, an electric vehicle, so we have achieved around 400-kilometer range. Vehicle range is nothing but how far a vehicle can travel upon complete charge. Like for the complete discharge, how far it can travel. And the cost of electric vehicle batteries have also fallen over the past decade. So when it comes to electric vehicles, we don't have many complex system like combustion engine, fuel tank, etc. It's just the battery and the motor. So the main cost of the electric vehicles relies on how costly the batteries are. So if we can come up with cheaper and more efficient batteries, the cost comes down, which is an ongoing process. And in the past decade, it has fallen by around 87%. So coming to lithium-ion batteries, so in the top figure we can see a typical structure of a lithium-ion battery. So we have cathode, anode, and the porous separator, and the matrix is filled with electrolyte. So the anode is basically made of is a lithium plus graphite matrix. So there is a process called intercalation in which lithium ions sort of get inserted between different layers of graphite, and they come out without having any much impact. So cathode has lithium metal oxides. So widely used material is lithium cobalt oxide. Some people use lithium iron oxide or manganese oxide as well. And electrolyte is made up of lithium-rich salts which are dissolved in organic solvents. So typically they use the Li3N dissolved in ECDMC, which is ethyl carbonate and dimethyl carbonate. Working principle is that the whole process relies on how lithium ions shuttle between the electrodes. So during discharge, what happens is the lithium ions lose the electron. Lithium atoms lose the electron, become lithium ions. The ions go flow in the external circuit, and the ions flow through the electrolyte and the separator and reaches cathode, and vice versa happens in the charge cycle. So this is a very simple and quite simplified explanation of how batteries are constructed and how they work. And this is a small representation of how lithium ion batteries have evolved over time. So as I said, cobalt has been widely used so far. So if we take our phone batteries, for example, it's highly likely that they have used lithium cobaltate as the cathode material. And cobalt is quite toxic and not very eco-friendly. So much effort has been put into reducing the content of cobalt. In that regard, people have come up with silicon batteries and nickel-based batteries. And we can also see how the energy density and specific energy density have improved, and the predicted energy density is very promising. So for the next decade. Okay, so these are some of the battery capacities used in all electric and hybrid cars. So all electric cars are the ones which run purely on batteries. Hybrid cars run on both fuel and battery. So the non-plug-in hybrid cars are the ones in which you can't charge the battery externally. They get charged by another device inside the car itself. And plug-in hybrid cars are ones in which you can fill fuel, which is petrol or diesel, and also charge the battery. And all electric cars just have battery. You just have to charge, and that's all. There's no question of fuel like petrol or diesel. So here we can see how the batteries are actually placed in an electric car. So so in the chassis itself, they are planted like below the seats. So coming to the crux of the topic, lithium-ion battery fires. So this is a quite familiar image which came up a few months ago, and it really raised the concerns among Indians, basically, because India is a tropical country. We are exposed to a lot of heat, and the scooter just caught on fire, which really had an impact on electric vehicle future in India. Okay, so these are some of the mechanical causes of or handling causes why a battery might catch fire. So design flaws are like, so basically the batteries are designed specifically for each vehicle, and based on the vehicle's design, they design the battery. And if the design has some sort of shortcoming, it is highly likely that the electrodes might come in contact and get short. And even while manufacturing, if the packaging is not proper, there are chances for short circuiting and improper disassembling. So if we feel the battery is not working, it's a very general instinct for us to open up the battery pack and do something with it, which is very wrong, because if we are not opening it properly, we might just make the electrodes touch each other, which will just generate a spark and start a fire. Mechanical damages. So collisions or high impact movements, or dropping a phone, for example, also has a good chance of starting a battery fire, because if the impact is high, if there's a lot of impulse, the electrodes might come in contact. And failure and tearing of the separator. So as we also saw earlier, the electrolytes are contain organic solvents, so they can decompose to form combustible gases, which will propagate the fire further. And charging in cold ambient temperatures, it's wrong, because in colder temperatures, the lithium will get permanently plated on the current collector. So when that happens, there is a possibility of dendrite formation, which I'll be discussing in the next slide. Overcharging is when we supply excess current or voltage, which is higher than the prescribed voltage or current, to charge the batteries, which might cause heating and subsequently start a fire. Inappropriate disposal is when we are done with the battery, we are not just supposed to dispose it as we see fit. So there are scientific methods in which we are supposed to properly dispose a battery. So electrical causes. So this is a quite interesting phenomenon that happens in lithium batteries. So this is the phenomenon of dendrite formations. So I'll explain it one by one. So here, this is a fresh lithium foil. So this is an as constructed battery, that is a newly freshly constructed battery. So in this, what happens is we have a gradual formation of the solid electrolyte interface. And here is where the discharge starts. So when the discharge starts, the lithium is being dislodged from its position, which is the anode, and it is traveling to the cathode. But while charging back, what we'd expect is that the lithium will come back and get deposited in this pattern itself. But that doesn't happen. There is a very irregular deposition of lithium when it is traveling back during charging process. So what happens is, if due to this irregular deposition, we have like small mounds and spikes which serve as nucleation sites for further deposition. So these irregular deposition points propagate further and further, forming needle-like structures, which are the dendrites. So dendrite essentially, they have the potential to grow so much as to touch the cathode, which will result in short circuiting. So here we have an SEM image of dendrite formation. So as we can see, this is the surface of the anode, and the dendrites are formed on top of it. So we have this very irregular deposition. We expect a uniform deposition, but that doesn't happen. So this is a very major issue when it comes to lithium-ion batteries. And thermal runaway. So thermal runaway are like temperature related causes, and overheating of a battery can happen internally or externally. So externally, when we are like overcharging the battery or expose it to high temperatures, and internally when there is short circuits due to maybe dendrite formation or anything. So this causes excess reactions, separator meltdown. So separator is essentially what is keeping the electrodes apart. So if the separator melts down, there is every chance on the planet for the electrodes to touch each other and cause a short circuit. And decay of organic electrolyte. So this was spoken a few slides ago, that the organic electrolyte can still decompose to form combustible gases. And also the cathode is made up of lithium metal oxides. So it's possible for the oxides to release oxygen, which is a promoter of combustion. So if there's a small fire that starts, it has a chance to spread to the parallel cells, and the corresponding cells will also start a fire, causing a chain reaction, which is called a thermal runaway. So how do we control the thermal runaway is by having an internal short circuit. As I mentioned earlier, uh, the battery is a series parallel connection of multiple cells. So if one cell fails or catches fire, if that cell is disconnected from the rest of the cells, we won't have this risk of thermal runaway. So we have multiple methods to have internal short circuits these days. This sort of summarizes what we spoke in the previous 2 3 slides. And moving on. So existing measures. So we have pressure vents in a battery. This works similar to the vents in the pressure cooker. So when the pressure is more, the vent just comes out, and the gases inside, which are pressurized, uh, get degassed. That is, they get released. So at high temperatures, when there is, let's say, leakage of electrolyte or something which may evaporate to form gases, the internal pressure will increase. And as we know, the batteries are packaged, the cells are packaged close together under some pressure. And if that pressure increases, it's possible for an explosion. So what happens is the vent just comes out and the gases get degassed, and separator serves as a fuse. So there's this material called polyolefin which decomposes to a non-ion conducting layer. So it basically forms an ion insulating layer when the temperature goes beyond a certain point, which totally shuts down that particular cell or the affected cells. And now coming to alternate battery architecture. So there are other batteries apart from lithium ion batteries which uh, can be used. So the first one in that, and the most promising one, is the solid state architecture. So as the name suggests, all the components are made up of are in solid state. So we saw that the electrolyte in the typical lithium ion battery has organic solvent, which is liquid essentially. But here we have sulfides, oxides, or polymer based electrolytes which are totally in solid state. So there is no scope of leakage or decomposition or something like that. And we don't need a safety layer. So it's not possible for uh, anode materials to just go and get shorted. So there is a solid wall between them. And the advantages of these are it has more structural integrity, so they are immune to mechanical damages. I mean, not totally immune, but considerable immunity compared to the traditional cells. And high resistance to dendrite formation. So it's not easy for dendrites to form, like pulverize through let's say a solid electrolyte compared to a liquid electrolyte, and low self discharge. As the reaction between a solid and reaction in a solid-solid interface is less, the formation of SEI is also less, and the self-discharge is minimum compared to a liquid electrolyte. They can withstand higher temperatures. Electrolytes do not decompose, as discussed, and they don't easily catch fire. And solids don't leak, so there's no leakage issues. Another architecture is anode-free batteries. So these batteries don't really have an anode. So there's just a cathode, a separator, an electrolyte separator. And what happens is the lithium ions get dislodged from the cathode and get deposited directly on the current collector. And from the current collector, the ions travel back to cathode. So we don't really have an anode as such. We have a deposited lithium, which sort of acts like, we can call it a pseudo anode. So, so that's how these architectures work. And the advantages of these are theoretically immune to dendrite formations, because upon uh, we would expect all the lithium that gets deposited on the current collector to come back to the cathode. We don't really expect anything to stick there. So if there's nothing on the current collector, there's no scope of dendrite formation. But in practical cases, it's not possible, as some lithium gets left behind and they serve as nucleation sites. There's no internal shorting because it just has one electrode, doesn't have two, and can be easily recycled. So challenges are these, like lithium may get permanently plated on the current collector, and this will lead to less lithium available for the subsequent cycle, which is decaying, which decays the active material over time. and formation of thick SCI layers may cause battery to seize. So the solid electrolyte interface still forms in this case because of the reactions, and if this layer grows thick enough, it won't be possible to get a proper cycling efficiency. And another architecture is lithium sulfur batteries. So in lithium sulfur batteries, lithium acts as the anode and sulfur acts as the cathode. And lithium shuttles between these electrodes. So what happens is lithium ions reach the sulfur and form lithium sulfides. So, and that's a good advantage as well as a disadvantage of this cell. Um, So I'll tell you why it's a disadvantage, because uh, lithium is expected to form a complex of Li2S. That's all. But what happens is we have long chains of sulfurs which just gets reacted with lithium, forming Li2S6 or Li2S8. So we can see that the efficiency of sulfur is sort of coming down when it comes to hosting lithium ions. It's quite an intricate concept, but you can understand that sulfur is not being efficiently used. So that's called polysulfide shuttling. So lithium forms polysulfides, which reduces the efficiency of the active material, and which this also results in decline in active material available and high probability of dendrite formation. And sulfur is not a very eco-friendly material, as we know, and that poses a challenge. Uh, then So implementation of these batteries are actually underway. So we have a company called Oxys Energy based on UK, and they are front runners when it comes to lithium sulfur technology. So they have collaborated with a company called Bio Aerospace, which are based in Colorado, and they have come up with a plan to construct an all electric aircraft, which works on lithium sulfur battery. So this is under development, and we have all solid state battery, which is in the prototype stage, and Toyota is sort of the front runner when it comes to electric vehicles at this juncture, and they have 1331 known patents on vehicle batteries. They are developing an all solid state battery for cars, which will increase the capacity and the range, etc., of cars. So they have promised to come up with a battery with a capacity of 1000 watt hour per kilogram within the next decade. So conclusion, so battery technology is quite essential for future electric vehicles, and lithium ion batteries is not the end, but sort of the beginning when it comes to electric vehicles. So there's a lot of future scope, because we need batteries with higher capacities compared to lithium ion batteries to deliver to, let's say, electrifying the entire traffic in the world. And battery fires are a major concern when it comes to lithium ion batteries, and this of course will concern, at least the Indian consumer market is very much concerned about going for electric vehicles due to these factors. And we have alternate architectures like solid state architecture, and this can be incorporated with anode free and lithium sulfur architecture to deliver safer and batteries with higher capacity. So in case of battery fires, so let's say back in 2008, if you were owning a Samsung Galaxy Note S8, so that was very susceptible to fire. They had to roll back the entire issue. So in case you come across a lithium-ion battery fire, call the fire department, and as a first aid, you can use Class D extinguishers, which have copper powder. And that's all. And that's it for me. I can take a few questions. No, no, not yet. So solid state batteries have their own shortcomings, which are limiting their usage. In, no, there's a very minimal risk of fire when it comes to solid state batteries. Yeah, sodium ion batteries can be used, but still, sodium, as we know, is still a very reactive material. It's very similar to lithium. So the chances of it catching fire is almost the same because if it's exposed to even a little bit of water vapor, it reacts rapidly. Li2 plus. There is Li2 plus. If you're referring to polysulfide shuttling, lithium forms polysulfides with sulfur. That is Li2SN, where N can assume values between 2, 4, 6, and 8. Yes, sir. Pardon, sir? C rate, solid state. Uh, would it reduce the C rate of the battery? Uh, I'm not sure. It can. Pardon? No, no, it's not going to 1000 watt hour. The battery used in this is close to 500 watt hour per kilogram. And they use some sort of fast charging technology which enables that charge rate. But again, now that doesn't mean the battery will last long. So that's why it's not in use. It might last for 2, 3 cycles, after which the battery fails. So they're still in the prototype stage. Yeah, there might be like electric fuel stations, so which supply electricity. That's a topic for another discussion. Yeah.
Maybe they are looking for an alternative for the fuel. Sorry? They are looking for an alternative for the hydrocarbon fuel. I think Robert sir wants to give advertisement for hydrogen actually. That's why. This is how you produce? Energy is needed. So they are doing good. So they do hydrocarbon burning and then produce.
In India, there are like 5, 6 cases reported in the past 2, 3 months. No, 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 no. Ola, Ampere, Bajaj, Chetak in some place, and I'm not sure if I'm allowed to name the companies, but yeah, multiple companies have had battery fire issues. They use similar technology, but I wouldn't say the same because each company has its own patented battery, so they'll have some modifications inside. So what could have led to the failure is not investigated, but around 6 cases of battery fires and 1 fatality has been reported so far.
Some electric scooter companies, they just buy batteries from some other company. But Ola is not doing that. Ola is making their own batteries.
Ola and Ather are making their own batteries.
Putting lots of support in supporting this.
Yeah, they're making. Whose?
Yeah,
They haven't reported.
Research lab to solve this issue because this is the main issue. Yeah, they have a lot of money in even in that lab also. Yeah.
And how do you by car and all?
For a phone to start with, we are looking at somewhere around 1,000 cycles of charge and discharge. So for car or bike, we will expect yeah, at least 1,000. Yeah, it'll come for 3 years. Yeah. So for cars and bikes, I don't own an electric vehicle, but I'm sure they get it replaced. Do you have an electric? Do you have an electric vehicle? Yeah. So yeah, just like getting a regular vehicle service, they do change the batteries, but I'm not sure for in what interval. Yeah, there's just battery. There is no other component. So that has to be maintained or replaced. Cost of changing a battery, that would depend on the company, the retail price. I'm not sure actually, but somewhere comparable to like 8,000 or something. I'm guessing. I'm not sure. Yeah, it costs 8,000. Changing in the sense you're not going to change the entire system.
Like our gas cylinder. Okay, we give back, we give a battery. That thing, so that should be our future. We are going to we are going to a pump. We are keeping our battery there and taking their battery and go. Because we don't have time to charge. It's a very good chance that we just go back to it. How you know? Because batteries like it, even if charge, everything. Correct. And how you will reach the death free. Right. Suppose that you have to choose a company, like we choose an LPG cylinder. You have to choose a specific company which we trust. I think that even charge discharge rate depends on the battery. Because the same age, same specification. How much it costs from the maximum charge to death rate, death charge level. So in that level, it is depends upon the battery configuration and modernization. It will be different. Not that easy possible. I may have a very good battery, and then maybe you may get a different battery. The main purpose of using or opting for EV vehicles is like reducing the consumption of hydrocarbon sources, like eventually reducing the pollution associated with it. According to what I read, like making these batteries itself is a huge pollution. So isn't that like going around the same circle again?
That would depend on the type of battery we are actually using. So if you're talking about lithium ion battery, yes, of course, it will have environmental impact as it is using cobalt and other things. So if we are using the alternate materials, sorry, in place of lithium ion batteries, like alternate architectures, so it's possible to develop batteries using less harmful materials. And also there are different procedures in which you can make a battery. That also can be researched into for having let's say a synthesis process with less emission. And yeah, so when you see the amount of hydrocarbon being burned by all the vehicles, I don't think the manufacturing one battery to replace the hydrocarbon burnt by one vehicle in its entire lifetime would actually be comparable.
And one more thing is that you have to recycle the battery. Then only, I mean, uh, now we don't know how to dispose a battery. Even our small batteries, AAA, AA batteries, we are just throwing it, right? We don't have a mechanism in India to collect the batteries and you can reuse the materials. Because the materials are not getting actually spoiled. You can reuse the materials. In the US and all, there are specific companies. You can give your batteries to them and they will take all the materials which are already used, and they can go for battery manufacturing again. So the recycling also should happen properly. Then even that environmental effects we can still reduce. Yeah. I don't know whether they are accepting batteries. I think there's one box to not one. Yeah, we know the box, but after that, what happens? I don't know. That should happen. Might be happening because DST, recently I saw in DST code, specifically they are asking for technologies to reuse recycle batteries. So,
Then we are going to go and check like how they are.
yeah.
But after some of the years,
I think that may happen. That may happen soon. I think whether you can use this in UPS. It's not in vehicle. They want to use it in the house. What is your suggestion? So then, UPS like the house. Buy a car, get the battery, use it. Whether you can use UPS or in the house. So connect the main from the house to the yeah.
any further question? First year students, I usually students are first year, second year, or third year. Any question?
If you don't have any more questions, we would like to thank Karthikeyan for the wonderful talk. Thank you, Karthikeyan, for the talk, and thank you for participating. We'll be again next week on 25th. Dr. Govind will be giving you talk. Thank you very much.
Yeah. Was it okay?
Thank you.
Was
from
it
the heart.
was it okay?
Very good.
Okay.
Take it a challenge like you can explain some rest of it. Okay. Thank you. Thank you so much.
I'll have to answer myself.